Yeah, my name is Christian Chilikov. I'm a digital design engineer at Semify. Today I'll be talking a little bit about dynamic CDC verification and what it is, why we do it, and also then presenting a model that Semify made, which is fully open source and licensed under the MIT license, so anybody can check it out and look into it. So let's get started. So we'll talk a little bit about what dynamic CDC actually is, how it's different from static CDC, what we're trying to verify, and then propose some approaches for dynamic CDC, as well as at the very end, present the model that Semify has developed. And yeah, let's get started. So what actually is dynamic CDC? It's essentially verification that's aimed at applying metastable stimulus dynamically in a test bench environment to a simulation where this metastability is injected into CDC crossings so that the changes in synchronization latency can be at the data output of the synchronizer can be observed. That's a little bit of a word soup. We'll talk a little bit more about what all that means in some of the next slides. But in short, some of the differences between dynamic CDC and static CDC is that dynamic CDC requires a test bench and a simulation to actually run, whereas static CDC just analyzes the design of your RTL to check for things like missing synchronizers or reconvergence issues there. Something kind of important to note is that static CDC does leave some holes purely because there's always going to be some sort of designer imposed constraints. And anywhere where there's some sort of human intervention, there's possibility for error to arise. Dynamic CDC kind of aims to bridge this divide because once you have a good model, it will always inject metastability into any synchronizer that you instantiate. So what exactly are we trying to verify? That the host or the physical synchronizers that will be in silicon behave in such a way that is accounted for in simulation. And that the design then functions correctly due to varying synchronization latencies caused by metastability within these synchronizers. And as I mentioned earlier, this fills some of the gaps left by static CDC, where there could be some sort of potential bugs that are masked away or hidden. So dynamic CDC is a really nice complement to static CDC, but it's not the end-all be-all. In particular, there are some challenges that come with it. For example, big drawback of dynamic CDC is that if a synchronizer is not actually instantiated in your design, then they could be left out and there will be no metastability modeling there. So you could have a dynamic CDC regression that's passing, but there could still be potential bugs that are hidden away because you didn't properly declare a synchronizer somewhere. This is a pretty big issue. It's one of the main, in my opinion, limitations of dynamic CDC. Also, it's limited by test coverage. So if your test bench is bad, it's very possible you can't exercise all the possible bugs that could be found. Additionally, integrating that into some flows can require some upfront efforts if you're doing this by yourself, especially when it comes to large designs. There, it's very possible that you don't always declare, let's say, a cell for a synchronizer, and you have this naive way of synchronization where you just declare 2 flip-flops, for example. And earlier I mentioned this synchronization latency. What I mean by this is that synchronization latency is the time it takes, or rather the number of triggering clock edges it takes for an input signal going into a synchronizer, a transition going into a synchronizer, to be seen at the output of that synchronizer. And why this is important is because in a regular RTL simulation, the synchronization latency for any 2D flip-flop synchronizer will always be 2 clock cycles. And this is because a regular RTL simulation doesn't really know anything about setup or hold times, and therefore it can't actually model metastability in any way. We need to do this ourselves, and this is where the metastability model comes into play. One more thing that I want to mention is that for the purpose of the presentation, whenever I refer to like the metastability modeling, it's always going to be within a 2D flip-flop synchronizer. And the reason for this is because any other larger synchronizers or synchronization schemes that you can make will fundamentally still use this 2D flip-flop synchronizer to handle the metastability in some way, whether that be like a FIFO or handshaking. The control signals will still be going through some 2D flip-flop synchronizer. Of course, you could add more stages there, make it 3 or more stage, but there will always be some sort of like control signal going through there. And this is where you want to model the metastability, because this is where the synchronization latency may vary due to metastability. And I'll show that a little bit more in the next slides. So how does metastability actually behave on a high level in hardware, right? Consider these 2 cases. So if you have something like a hold violation that occurs in a synchronizer, or for the data going into a synchronizer, Assume that the data will settle to the new value, right? This is one of the possible cases. It can settle to the new value or the old value. Assume it settles to the new value. There's a hold violation. Flip-flop 1 goes metastable. Before the second flip-flop captures it, it resolves to the new value, and the second flip-flop captures it at the next cycle. So there's essentially a 1-cycle delay in data. This can't happen in RTL, but it can happen in physical hardware. Same thing for a setup violation. If there's a setup violation, the data resolves to the old value, then there will be a 3-cycle delay. Again, this can't happen in hardware. We have to manually model this. In simulation, for the exact same cases, what will happen is that the simulator resolves the value at the delta cycle prior to the positive edge of the clock or the triggering edge of the flip-flop. So there will always be this exact 2-cycle delay. So we need to bridge this gap somehow. We need to model this in some sort of way and take this into account. So there's 2 ways to do this. You could go the custom modeling way and make a model by yourself and figure out the logic for this to inject metastability, or take a model that already exists. Or you can use proprietary tools which do this automatically, things like CDC, for example. And there's trade-offs to both, of course. So doing this by yourself, you're never going to get all the benefits as with proprietary tools. So it does turn into a game of like weighing the pros and cons. Proprietary tools are quite nice because there's really usually no effort needed to integrate this sort of dynamic CDC into your synchronizers. It'll just automatically detect synchronizers and inject metastability in there with your test benches. But on the say drawback side, a lot of these tools are very expensive. If you create a custom model, what you can find is that it can be quite versatile, let's say, and nice, but there's a lot of upfront effort to do this sometimes, and also to add all the synchronizers into your design and make sure that all synchronizers are present in your design. But on the positive side, it is free, and it's something that I think is manageable to do, especially even so if you're a small team. I think it's still quite feasible. So with that being said, what are some ways that we can actually model this metastability within synchronizers? There's a few naive ways of doing it, I think. A common one, which I've actually seen before, is this window method, where you try to get as close as possible to physical hardware, where you say that there's going to be some sort of setup and hold window around your positive edge. And if there's a data transition in there, then the value will randomly resolve to a 1 or a 0. And upfront, this seems pretty good, but there are some drawbacks to this model. For example, here it's actually quite difficult to scale this with large designs if there's lots of different clock domains, or if the periods of the clock domain is changing. Not dynamically, just if there's different clock relationships. The reason why is because you have to then make some windows bigger or smaller. Otherwise, the chances of metastability happening are actually quite low. And it's not pessimistic enough. That's really what it comes down to, is this sort of modeling is not pessimistic enough. And you can't really control the amount of pessimism other than just manually making the windows bigger or smaller. And we kind of need a more abstract way to model the worst case scenarios rather than just hoping metastability gets hit more often. And that's kind of where Semify made our own model that we released, where it does this sort of pessimistic modeling by determining when it's actually possible for metastability to happen. And if it's possible, it will happen. And you can control this level of pessimism as well. But the main distinction there is that there's a lot of checks that go on behind the scenes to determine if it's possible for metastability to occur. And if it is, it will auto skew the data inputs to force setup and hold violations, while still ensuring that this sort of scenario could actually happen in hardware. So the idea there is to avoid these false positives and avoid saying that like bugs could occur if they actually can't in hardware. This was one of the main things that we modeled this with. Additionally, it's very parameterizable, so the model scales quite well with large designs, as well because the parameters could all be set at runtime. There's no need for recompilation, which is quite nice. Additionally, there's black boxing, so you can black box certain hierarchies and run dynamic CDC only on certain parts of your design, which is quite nice as well. Again, no recompilation needed. And the nice thing is that once you have this model and you instantiate it somewhere in your design for all synchronizers, there's a switch to make it synthesizable. So without having to change any RTL, just by changing a parameter, you can either synthesize your model if it's for an FPGA, or you can run a dynamic CDC simulation, which is quite nice as well. And yeah, as I mentioned earlier, then these 2D flip-flop synchronizers are used to build some more complex synchronization methods. So you can use these in the control signals of FIFOs, for example, or in handshaking for things along these lines. The repository is linked here in the slides. There's some more technical details there as well, if anyone is interested. Again, free to use, free to check out. I think this is all I have for today. Thank you all for listening. Yeah, appreciate everyone being here.
Any questions?
Have they
Yes.
been used in real projects? The models?
They have, yeah. Yeah, so I worked on developing a different model for a different client, and that one was actually used for a pretty big SOC. There, I was not actually responsible for running the dynamic CDC, so some of the issues that came up, I helped with debugging. I actually didn't find any real issues so far that static didn't check, but I found some false things that came up, but that had to do with the way the things were instantiated, kind of a long story. But this has been used in real hardware, similar model, but yes, in short. Yes.
Do you have some data on what's the simulation impact with the model that you have?
Yeah, that's a very good question. Actually, something I didn't get into. So I mentioned this model is pretty good for large designs. Part of the reason why is because the overhead impact of using this model compared to just a standard 2D flip-flop synchronizer is actually quite low. So in the repository, I did some benchmarking, and there I found that by using the model with like all the extra features, there's like a glitch monitor in there as well, which does some background checks. It was less than an 8% overhead compared to just a regular 2D flip-flop synchronizer. This becomes pretty negligible when you like also consider the fact that synchronizers themselves are a pretty small part of the design too. So it's an extra 8% on synchronizers only, but that's quite small in the grand scheme of things with when you have other logic as well that you're interfacing with. Sure.
You do this at the gate level with timing or what level of abstraction do you run this?
Yeah, that's a good question. Gate level is kind of a separate thing. So you can actually catch basically all of these issues in gate level. I think all of these issues you can catch in gate level. The idea there, though, is that with gate level, you're still operating on like the kind of naive modeling that I showed, where you have a setup and hold window. So again, it's not pessimistic enough. Gate level is also very slow compared to just doing this, right? So the idea here is you still run an RTL simulation. It's still very fast, still very lightweight, but you also do some CDC checks as well on top of that. And you make it more pessimistic than what a gate level simulation would be. So with the idea of hoping to find some hidden bugs. Yeah, good question. Yeah.
So maybe just trying to understand the model. Does it do pulse swallowing? So you can swallow a pulse.
Also a very good question. So with a naive modeling, there's another way you could do this where you say on every data input, for example, there you randomize the first bit of the synchronizer. But this does exactly what you say, where it filters out certain data, which is really bad because then you lead into these like false positive bugs. This would never happen in hardware.
Pulse being swallowed is a good thing.
No, it's not a good thing. Fully agree with you. It's a very bad thing, especially if the pulse is like bigger than the destination clock domain period plus like setup and hold. This would never happen in hardware. So there is checks within this model to make sure that if there is a transition and it's held for long enough, it will be seen in the output. When it's seen is like variable. It could be 1 cycle or 3 cycles, but it will be seen at the output, just as it would be in hardware. So this was something that was accounted as well. Does this answer your question or?
Yeah, okay.
Sure, we could also talk.
I think in hardware you would, the room can correct me, you would probably swallow a pulse in terms of if I put pulse into a synchronizer, there's quite a good chance that it won't come out the other side.
Sure. When you say pulse, do you mean like a glitch? Or?
So like a single cycle. So if I put a single cycle into a synchronizer,
right,
there's a chance it would make it out the other side in both RTL and in hardware.
So if, again, please correct me if I'm wrong, but if this pulse is in period longer than the destination domain clock cycle, the receiving domain, plus the setup and hold time, then there will be at some point a time when it is sampled without the chance of metastability to happen. I think this would be easier to maybe draw out. We could talk after as well.
Metastability.
We
have a lot of comparison, right? And it's maybe 100 lines per hour. Number of hours we spent debating and analyzing this,
definitely. This seems like very simple, but it's actually quite tricky when you start designing it yourself. But this was an issue that I ran into when like designing this for client was the model that they were using actually had this filtering that was happening, which was exactly this, where data was being filtered when there was a pulse, and it was incorrect because this sort of issue never happened in hardware. And you have to then go and correct the model and figure out like why this was an issue in simulation and not in hardware. But yeah, it's definitely a tricky topic.
I think
Thank you.
possibly what you're referring to is when you've got a pulse, a source clock that's very close to the frequency of the destination clock.
Yes,
So if it's metastable on the first sample edge, it's likely to be metastable on the second one as well.
exactly.
And therefore you can swallow the pulse sometimes.
Exactly. So in this
Well,
case, absolutely.
Yeah, in that case, I would say you need to redesign the circuit so you don't have that problem.
Yeah.
Because that's actually a real
That's the
problem.
block, right? Yeah.
Yeah. But in this case, again, if it's bigger than the destination domain clock cycle and the setup and the hold time, then at some point there will be a period where it will be sampled correctly. But this is a very good observation. It's a very tricky edge case to handle.
Is the code for the model synthesizable SV, or is it a kind of mix of class SV and real SV?
Yeah, good question. It's right now pure system Verilog, and there's just one parameter to make it synthesizable or not. This parameter, all it really does is just generate block, whether it's a 2D flip-flop synchronizer or actual model. So it's synthesizable, no UVM required, pure system Verilog. Yeah, there was one more question. Yes. Right now, purely behavioral. Of course, you could go and add cells to this, but I haven't done any work there on this so far. But I do actually plan on updating this as it goes. I think it'd be a lot of fun to add more and more different models for Dynamic CDC and just make them all open source. Yeah, thank you. Good question.
So I've probably got one comment and one question before we wrap up. So probably my experience is very similar. The number of hours, man years put into by designers asking us to model metastability as a verification team has been an absolute pit of resource for years. So it's good that someone's addressing it. How do you, given the scaling and the benefits of doing this efficiently, how do you see it? Do you see it scaling to emulation, where this could actually be a real win, given the clocking structure of emulators is slightly different?
To be honest, I don't know much about emulators, so this is my scope. Good. This is maybe a good conversation for afterwards. But when you say emulators, do you mean like hardware emulators?
Things like Velocity or Zebu or any of the hardware accelerator blocks.
Okay. Yeah, this is a little bit out of my scope. So
okay, that could be an interesting one because obviously as designs get bigger, this is a real benefit. So yeah, emulation could be a big win.
Very cool. Yeah, have someone to talk to afterwards. So very nice. Thank you.
Well, that's the last presentation. So thanks very much.
Thank you.
And yeah, I think lunch is downstairs.